This video looks at how you might formulate an MCAS for a dual mode approach with tracking. The previous video then explained the need to put limits on allowable targets to ensure the steady state was feasible, and that comes about because of how we've set up our dual mode control law, where we assumed that the steady state was USS and XSS, and we have to make sure that that steady state lies inside constraints. What this video is going to do then is consider a procedure for forming the MCAS, so that's the admissible set, which can be done offline, and here's the key thing, only once, even though the targets and disturbances may be changing. So what we're doing is we're going to allow these values USS and XSS to change, but we still want the MCAS to be defined just once. And you remember that when we defined it a few videos ago, the USS and XSS appeared explicitly in the calculations, and thus the admissible set was valid for only the given USS and XSS. So we want to relax that and see how do we go about it. What we're going to do is we're going to predict in absolute values rather than using deviation variables. So again, if you look at the earlier videos, you'll see we use deviation variables, and that is in essence what gave us the problem when we wanted to change the target or disturbance. Just a reminder then of what we said in the previous video. We said the steady state must lie in the interior of the sample constraint. So we came up with some conditions like this. I'm not going to repeat them, but the key thing is there's an upper limit on the difference between the target and the disturbance, and a lower limit on the difference between the target and the disturbance. In essence, you cannot just set any target you like or apply any disturbance you like, or the implied steady state will lie outside of your sample constraints. And so you need to check, so I changed the colour, you need to check the targets you want to use against these inequalities and make sure that they're feasible before you start. Dealing with infeasibility is a whole different area which we don't want to go into quite yet. We want to predict in absolute values because that allows us to change the target. So first of all, if you remember, we had this expression here which gives us a link between the expected steady state of the state and the input and the current value that you think you've got for target minus disturbance. And so we ended up with this formula down here, so a very simple relationship between the two. If we use that relationship and plug it into our predictions, then what you find is the predictions now have several different states. We've got the actual state xk, that's the bit you might think is easy, but implicitly we've also got this r minus d comes in here, and we've got your perturbation terms or your degrees of freedom ck here. So we've got three different terms in our prediction equation, and what we're going to do is keep hold of all three terms and allow them to be variable rather than fixing them. However, one of the things that you need to remember is that in the predictions we assume that the term r minus dk does not change, but of course when you move to the next sample it may change, so it's only during the predictions itself that we assume it's fixed. Now what I'm going to do is form, as we did in the early videos, an autonomous model which captures everything that's going on, and the key here is to include the target or disturbance estimate as an extra state in our autonomous prediction model, and that's the trick that allows us to do what we want. So here it is, and you'll notice we've got a state for this prediction model, and within that state we've got xk, our system state, we've got our degrees of freedom c future, and we've got this term rk minus dk. Now if I put that all together, you'll see I end up with this rather large, but that doesn't matter, transition matrix psi, which links this z from one sample to the next sample. But the key thing is it's autonomous. I've captured everything in a simple model which takes the form zk plus 1 equals psi zk. Now if I want to extract the input, then you'll see the dependence of the input on this state is given down here. What are the typical constraints I'm dealing with then? Well, we have constraints on the inputs, there they are, constraints on the states, and limits on the values r minus d might change. So next, what I need to do is put those constraints in terms of the same state z. So there we go, there's the state Z. And what I can do is I can do input constraints, that's that top block, state constraints, that's this block here, and the bottom block is our constraints or limits on R minus D. Now the key difference I'm going to do here is I'm actually going to split this constraint inequalities into two parts. You can see I've got this G1 minus G2. Now why am I doing that? And the reason I'm doing that is I know that within the predictions I'm assuming that the value R minus D does not change, and therefore these inequalities down here at the bottom cannot change from one sample to the next. And therefore, although I have to check ZK against constraints G1 and F1 for every sample K, actually I only need to check these constraints G2 ZK less than or equal to F2 at K equals 0, because it's not going to change thereafter. How does this change our admissible set? Well, what you'll notice if you look at the previous videos when we showed the admissible set structure, the difference is this top block here. Earlier in our admissible set you had a structure a bit like this. You'll see we had G1, G1A, G1A squared, and so on down, and here you'll see I've got F1, F1, and so on. The difference here is I've added at the top this G2 and this F2 constraints, but I've not iterated that through the dynamics A. And why is that? Because what I've noticed is that G2 a to the I zk is the same as G2 zk. So there's no point. So it's a very subtle difference, but you must do this, okay, or your algorithm will, this is the key thing, not converge. Okay, because essentially we've got this equation that R minus D is a constant. If you iterate forward on the G2, you'll find your admissible set never converges because that constraint set is never converging. So in summary, we've got a stable model of this form, zk plus 1 equals psi zk. We've arranged our constraints in this particular form where we've separated between ones that actually occur every sample and ones that occur just once. And we need the asymptotic point, the convergence point, to be in the interior. Now once we've done this, we can apply a relatively standard admissible set algorithm as long as we recognize that the G2 constraints do not change, so we don't include them in the iteration. And this point down here is important, because otherwise your set algorithm may not converge. Now we've given you some code for doing this, and you'll see it's in this file here, find MAS_tracking.m. Okay. When we've gone through that code, we're going to end up with an MCAS, which is given with a formula a bit like this: f zk less than or equal to t. You might prefer to note that f can be separated into an m, an n, and a v, and therefore write your MCAS in this form: nc future plus mxk plus v into r minus dk less than or equal to t. And you'll probably find, as a general rule, it's more convenient to put it in this form once you've calculated it, but you need to start with this form in order for your admissible set algorithm to work. The other thing you'll note is the shape of your MCAS is closely linked to the value r minus d. You can see it's got this term in here. If you change r minus d, then the admissible space for x is clearly going to change. And just a note at the bottom, you'll see reference governors make use of that observation. So we've provided some code for you, and it's in this file, find MAS_tracking.m. The code is simple and transparent, but here's the key warning: it is not efficient by any means. It's just there for illustration to get you started. However, if you have a slow system, that's with slow polls or lots of states and so on, then you'll find it's rather inefficient and it will be very, very slow to converge. So what I'd recommend is, in the long term, you need a more effective algorithm which removes redundant constraints, and we'll look at that in the next video. So what code have we provided, just so you can look at things and see what's going on? So we've got this file here, chap5_mpc simulate constraints c, and that runs the file find MAS_tracking.m. We've done two examples for you to look at for this video, video 513 example 1 and 513 example 2, but you are warned that this second one is very slow. It can take a minute or 2 minutes, so if it seems to be doing nothing, just be patient, and that's because the algorithm for finding the admissible set is just not efficient enough. Okay, so these are the results that you'll get out of video 5.13 example 1. Now what I'm going to do very briefly, I don't think we really need to run it, is just show you what this code looks like in case you want to play with it. You'll see that we've got an A, B, C, D, we've got our Q and R, standard as before, and C, we've got our constraint limits. Everything is very simple, your standard form, so you can play with it if you want. We've got a check for the target being feasible. So checking that R minus D within sensible limits. We define a reference, a disturbance, an initial condition, and then the key call command is this one here in line 37, and then a number of plots. Now the key plot you're going to get is this one here, and what you'll notice is we have a target change here, and at this point here we have a disturbance. So what you'll see is that we've only calculated the set once, and this set has dealt with the fact that the target might change or the disturbance might change and can change at any time, and that's the simple illustration. And the other thing you'll notice, of course, it converges to a steady state which is not at the origin, and it converges to the right value, and the right value being 1. You can see this is converging as expected. You can see that the cost J is Lyapunov as expected, as long as R is constant or D is constant. Video 5.13 example 2, and here the key thing to note is this is very, very slow to converge and has a huge number of inequalities, 644. Now you will find that the vast majority of those are redundant, but there's no checking for redundancy in the find MAS tracking algorithm, because we're worrying about that detail later. But the key thing again you'll notice is it's got a target change and it's got a disturbance, and everything works as expected. So in summary, this video has shown how a single MCAS can be constructed for the OMPC-OSMPC algorithm, but critically this MCAS embeds the possibility of time-varying targets or disturbances. And the way we've done this is we've basically added the target and disturbance signal as an extra state within our prediction model. However, the target must be reachable, and in fact it also must be feasible during transients, which is another subtle issue. So you've got to put limits on the target in the algorithm, because otherwise your admissible set algorithm will not converge. The code is not efficient, and convergence is very poor, and it can fail altogether if you don't put appropriate limits on R minus D. But remember, this is for illustration only so far. And just a reminder that ensuring feasibility is actually beyond the remit of this chapter.